Folks, I am very excited to welcome you to Stephen's PhD defense. As many of you know, we begin these defenses traditionally with a little bit of an intro from the advisor. Although in this case, I felt like perhaps more of a trailer would be appropriate. You might think of Stephen's PhD as sort of a great caper. So, you know, it was a dark night at a university that knew how to keep its secrets. But on the second floor of the Gates building, there was one man still seeking the answers to life's persistent questions. And that man was Stephen Lyubomirsky, Private Eye. Now, from this slide alone, anybody who knows Stephen realizes there's already a mystery. In particular, how did anyone get a picture of Stephen without a tie? I'm not sure. Now, our intrepid detective, Stephen, marches to the beat of his own drum. You know, compared to other detectives like Sherlock Holmes, who always has a pipe, or the famous Marlowe, who's never far from a smoke, Stephen takes a slightly different approach to things.
I remember this one.
Another way in which Stephen is different is that typically detectives are tasked with investigating crimes to uphold the law. Instead, Stephen writes his own. But actually, in all seriousness, Stephen has been an incredible leader in many of our projects. You often see him as the one, you know, organizing the meetings, taking the notes, guiding people, figuring out what needs to be done. And in our own meeting notes, I think over the course of the PhD, I recently did a count. I think Stephen and I have accumulated something like 300 pages of notes from our meetings. So a lot of voluminous leadership in figuring out the right way to run a PhD. In fact, his principles for leading research projects have become so successful, they've been encoded literally in stone. Now, there's another mystery from this slide, though, which is what's up with this guy's background, right? If you go look at his websites and talks, you see a lot of amazing visual appeal. But this perhaps shouldn't be surprising. After all, Stephen's background is that he's from Princeton, where he was summa cum laude, magna cum laude?
Summa cum laude.
Yeah, that one. Now, as you can tell, we have slightly different backgrounds. For my own, in my own experience, the first time I saw Paisley was, or the only time I saw Paisley was on one of these. So in honor of Stephen's aesthetic sense, we're going to switch backgrounds for the rest of this slide deck to more match a hybrid of our styles. Now, Stephen, as a great detective, is of course also a master of disguise. So one example of this that I'd like to show is an intro to one of his.
What's boppin', hep cats? The night is young and I am ready to jam. Except all the disco clubs are closed because of the novel coronavirus. Could you believe that? A cool cucumber like me stuck here at home? There's hardly any room for my bell-bottoms.
Dance floor is full.
Sometimes, though,
But that's
even
not
when
all.
the clubs are
There's
open,
another instance, just to give you.
I am a non-attorney spokesperson, and I have news for...
Oh, wait, is this one of those commercials? The last time I bought one of those products, my dog's hair fell out.
Now, I believe the terms of the settlement included a non-disclosure agreement, if I may remind you.
So, am I going to read the terms and conditions?
Terms and conditions, you say? Why, no, young architect! The 3LA methodology will let you define your terms
Okay,
and verify
no spoilers.
them too.
But Stephen is a master of disguise, not just in giving amazing research talks. Don't worry, there's no video on this one, Stephen. Not just in giving amazing research intros and compelling skits to what he's talking, but also in the computer science community, Stephen was the key writer for all of the most recent student skits. It has 2 or 3. So here's a picture of him leading and also acting as Ed in one of our skits. And as we all know, sometimes things get rough. Stephen can also certainly hold his own. Here's an example of him participating in a TGIF where he won a boxing match with Rock'em Sock'em robots. But these are all examples of, you know, Stephen really being a pillar of our community here. We've been very lucky to have him, whether it's celebrating after a lot of late nights for intense deadline pushes, or recruiting and mentoring several undergrads in his projects over the years, or going to Pulse Hangouts with the groups and, you know, helping everyone feel included and welcome. Stephen's been absolutely an amazing member of the lab. And, you know, as you're going to see in his defense, as a great detective, like any great detective, Stephen always gets his result. So here's a photo of him where he's won basically every award he could win through Ada Center engagements.
Slight exaggeration.
He's sort of weighed down, he's burdened with all of his success. I guess he doesn't have the Liber Americas plaque here. But really, Stephen, we are so grateful to have had you do your PhD with the group, and we wish you all the best of luck. The main mystery left for us is how we will continue to survive after you ascend to post-PhD life. So thank you so much. And with that, I will turn it back over to you.
Audio safe for me to switch?
Yes.
I lied.
All right, well, thank you very much, Zach. That was a touching introduction. I knew when I made all those videos that they would be blackmail material. I did not realize just how far you would take it, but truly I'm touched and flattered, and the greatest reward of all is, of course, this one. Thank you, Zach, truly. So as I set up, I'd like to thank you all. Thank you all for turning out in such numbers. I'm happy to have many of my collaborators from other institutions here, including Professor Arti Gupta from Princeton. Is Sharad in the call as well? Professor Sharad Malik from Princeton. It would take me too long to name everybody, but I'm very happy to have my external collaborators here. Excuse me as I share my screen, and I'll get started with the presentation. I think we're ready to get started. If there are no objections, the committee's present. So we can begin. Thank you, everybody, for turning out in such numbers to my PhD defense as I present to you my dissertation on compiler and runtime techniques for optimizing deep learning applications. What a mouthful that is. And the slide doesn't change. Artificial intelligence is a notoriously tricky term to define, but for a long time, experts have had a clear idea of what artificial intelligence should look like, namely systems that take in information about the world, process it according to some kind of set of principles which are carefully articulated, draw conclusions about the world, and perhaps even act on those conclusions and affect the world. This is the classical view of artificial intelligence, and it has been an enormously productive intellectual lineage. Many of us every day use work that stems from it, as any of us whose research involves SAT solvers can attest. And in many problem domains, the classical approach has been very successful. For example, just about anybody in this room can write a chess-playing program that could beat any human master with a fairly simple algorithm that builds up trees of game states and prunes those trees based on heuristics. It's in every AI textbook these days, and it'll beat any human master, trust me. But there are other problems where the classical approach has more difficulty, where being able to articulate principles can hit some limitations, and a famous example of this is images. Images can be staggeringly complex. The human ability to make sense of them is oftentimes remarkable, at least from the perspective of classical AI. An image can be taken from many angles. 3D scenes can be very complicated, and yet we often make sense of them. But for a computer to do so, another approach has proven more successful than classical AI techniques, namely that of statistical machine learning. On this slide, I will go through, I'll give a high-level summary of the neural network technique, which can be used for many things, but in this case, I'll talk about processing an image, recognizing which pixels in an image represent a human face. In the top left, I have a diagram of the perceptron, which is a linear classifier developed in 1958 by Frank Rosenblatt. And the perceptron it's a fairly simple but very versatile little algorithm. It takes in some number of input features, which are just numbers. It computes a weighted sum, where the weights are parameters that have to be specified, and it passes it to an activation function, which returns a classification. So essentially what it's saying is which side of a hyperplane are your features on, which side of a line are they on in n dimensions. Very simple thing, but remarkably, if you connect many perceptrons together in a network where you take the outputs of one, pass it to the inputs of another, with a sufficiently large network and the appropriately chosen parameters, it can compute any numerical function. Far from obvious and quite remarkable. And this can include numerical functions we care about, like which pixels in an image correspond to a human face. But of course, there are many wrinkles here. In particular, how do we choose the parameters? Well, this is where having many examples comes in. We have lots of data around us in the world. Any of us can take a picture with our smartphones. So if you have many pictures and you can indicate that they're of human faces, you can start with some arbitrary choice of parameters, figure out the error, the difference between the parameters you started with, the difference between the result you computed and the results you want, and use calculus to shift the parameters in a direction that reduces the amount of error. So essentially playing around with knobs until you get a setting that works. It's not a very romantic way of putting it, but we can do this automatically and at great scale. That's what the image at the bottom is depicting, this process of hill climbing, essentially looking for a local minimum. Of course, things are much more complicated than this story, but it's certainly good enough to recognize faces in an image. But we can take things farther, and this brings me to deep learning, which is the subject of my dissertation. So far, I have, when I mentioned the perceptron, I mentioned taking in some input features, which are numbers, but where do they come from? Historically, these input features came from manual processing. For example, performing a filter on an image to indicate where edges are, or even isolating parts of an image. This is all hard work. And of course, computer scientists are not averse to doing hard work sometimes, and plenty of AIs have been written using such approaches. But the idea of deep learning is to remove this manual step as well, and instead operate on essentially raw data and infer features in a way that can be learned from parameters as well. On the slide, I have a diagram of the famous model Linnet by Jan LeCun in 1998. This was cited in his 2020 Turing Award, and it's a nice little model. It was trained on a data set of handwritten zip codes from the US Postal Service, and all it does is look at a handwritten digit and tell you in digital form what number it is. It achieves very high accuracy, but it did so without any manually encoded notion of lines or strokes or curves or any of the features that a human might talk about when reasoning about a handwritten digit. Instead, it applies filters to the pixel values of the image, and those filters in turn take parameters which can be tuned by the same process of stochastic gradient descent that I described on the previous slide. So all you need to recognize digits is a bunch of linear algebra operators and the ability to get the derivative and adjust the parameters. It sounds very nice, but just how far can we take this? Why am I telling you all of this? Well, I am telling you all of this because deep learning is everything these days, and it is everywhere. On the slide, I have a question that a colleague, lightly paraphrased, that a colleague asked me in earnest: what today isn't deep learning? She asked because deep learning seems to be commanding the attention of researchers across many disciplines, not only coming up with models for deep learning, but also designing the systems that support them. And in the rest of this talk, I will tell you that there are very good reasons for all this attention. In particular, applications all across our day-to-day lives and throughout the economy are increasingly making use of deep learning methods. As long as you can cast a problem as a numerical problem, you can start to think about now how you might design models to begin making progress on those problems. And this has resulted in amazing progress in tasks like voice recognition. Of course, facial detection is an easy one, but even more complicated problems like detecting possible obstacles in a self-driving car, all of these are powered by deep learning applications, and plenty that I have not illustrated on this slide as well. These applications and the scales they run on have demanded the development of a vast computing infrastructure for processing all the data, training the models, and of course serving the applications. Again, massive data centers have been constructed to support these applications. And when you are operating at such scales, efficiency, both in terms of speed and power consumption, is a top concern. And an interesting bit of context here is that we find ourselves in an interesting time to be worried about efficiency in the world of computing, because as has been widely heralded, and you know it's been widely heralded because on this slide I am quoting a quote, it has been widely heralded that Moore's law is dead. Our ability to pack more transistors into a space and deliver power to those transistors is hitting physical limits, which means we can no longer efficiently scale up the same designs. So if you want greater efficiency, so said John Hennessy and David Patterson, in their Turing Award lecture. If you want greater efficiency with these limited resources, the answer is specialization, something that the field has taken up with enthusiasm. People have begun to design specialized devices intended to compute specific functions with as much efficiency as possible. And I want you to think for a second how massively expensive a task it is to design a new hardware device. Coming up with the design is not an easy thing, but there are still the further expenses of manufacturing it and implementing software support for it. These are massive expenses, and yet the scales of deep learning are such that these are justified. Many accelerators have been developed to speed up specific portions of even sometimes specific deep learning models. Such are the costs involved. At the same time, deep learning applications themselves are becoming more complicated and more expressive, demanding more complicated systems to support them. On the left, I have a diagram of AlphaZero, the game-playing AI that defeated Lee Sedol in Go. And AlphaZero is interesting because it combines a technique from classical AI, a Markov chain tree search, with a neural network that is used as a scoring function for different board positions. So it is combining learned functions with classical AI techniques, as does the model on the right, the neural symbolic concept learner, which takes as input an image and a question about the image, and it produces an answer. How it does this is it uses a neural network to produce a logical representation of the image, as well as a logical representation of the question, and then it applies symbolic reasoning from classical AI to produce an answer. So again, it's another instance of combining classical AI with learned components, and what I want to emphasize here is that the problems these types of models are dealing with are more complicated than the tasks traditionally given to deep learning models. Now we're talking about looking at an image, understanding what it is, and answering sometimes even multiple questions about what's going on in the image. So the sights are being raised for deep learning, and so and accordingly, the models themselves are becoming more complex to handle it. To take a step back and survey the systems landscape of deep learning, we see that deep learning systems have the enormous task of shouldering the burden of these increasingly complicated applications and ensuring that they can be run in the many different contexts that have to support them. This includes not only massive scales in data centers, but also sometimes low-powered embedded devices and mobile phones. So deep learning applications, again, they're finding their way everywhere, even into our own pockets. And this is a daunting problem. Many people have thrown their hats into the ring here, and I will count myself among them. In particular, in my dissertation, I contend that there is a useful framing we can use for this problem, that of compilers. A compiler is a program that takes a representation of some computation and lowers it into a form that can be computed by the appropriate target, and oftentimes by the appropriate hardware system, but not necessarily. It can be an abstract target. It doesn't have to be a specific system. And of course, deep learning is a problem, compiler's problem on a much greater scale than that. We have many questions about what is the right way to represent these increasingly complex computations, and we have a moving target when it comes to hardware, when it comes to lowering them. But I contend that the compiler's literature provides many examples from the past of techniques that can help us surmount these problems. It is not my original observation that there are some deep similarities between, pardon the pun, between deep learning applications and problems faced in general programming languages. Here I have a quote from the Turing Award winner Jan LeCun discussing the concept of differentiable programming, arguing that the more expressive sorts of models that I've shown you, like AlphaZero, like the neural symbolic concept learner, although that didn't exist at the time of this quote, that these could be thought of less as designing specific models, but as a form of general programming, the way we would write any other program, except with the new trick in our toolbox that we can parameterize these programs and use processes like stochastic gradient descent to optimize them. So he is encouraging deep learning researchers to be more creative in how they design their models. And the contention of my doctoral dissertation is that this view of differentiable programming applies not only to designing the applications themselves, but also to optimizing them and deploying them. That we can we can take hints from general programming languages when it comes to designing systems to support deep learning applications. And in particular, I contend that we can guide ourselves with precedents from the compiler's literature to aid in the optimization and deployment of deep learning systems. In the rest of this talk, I will support my thesis with 3 examples from across the system stack, ranging from a programming language for expressing deep learning models to system-level optimizations to the problem of lowering deep learning models to the appropriate hardware backends. I will use these systems to support my thesis and demonstrate to you how inspiration from classic programming techniques and the compiler's literature can help us reach new heights in deep learning systems. I will proceed to the first of these topics, which is Relay, a programming language for expressing deep learning models. I want to emphasize that I do not count Relay as a contribution of my dissertation because it was in fact the subject of the dissertation of Dr. Jared Resch, who I am grateful to have in the audience, but I worked with him on Relay. It is an achievement I am proud of, and it more importantly also guided the rest of my work. It helped me provide perspective, so I think it is necessary context for the rest of this presentation. Relay begins with the premise of what representation should we have for the growing complexity of deep learning applications. Historically, as I showed you with the diagram of neural networks, historically, deep learning models have been conceived as static data flow graphs, where the nodes in the graphs are tensor operators, essentially operators on giant arrays. Giant multidimensional arrays, and the edges just indicate which operator feeds which other operators. It's a simple mental model, one that's convenient for many applications, and it can be convenient from the system's perspective as well. It's easy to divide a graph into pieces and spread it across a distributed system, for example. But when it comes to designing more complicated applications, like say AlphaZero, a graph is insufficient. Right, in AlphaZero, you have a tree structure. There is control flow. There is dynamism. And these richer features demand, again, a language for expressing them. There are other issues when it comes to the lower levels of the system stack as well. Namely, in a graph, you lose a lot of high-level information. If you have a repeated unit in a graph, you have no way to know automatically that it's a repeated unit. You have to analyze the graph and figure out, oh, this is repeated here and there. We have to perhaps deduplicate it. That can depend on caching effects. So having a way to preserve such high-level information can be helpful for designing compilers and systems to deploy such applications. This was the premise we began with for designing Relay. We stated our goals, as I summarize on this slide, to preserve high-level information about a program, to facilitate more complex analysis of programs before we compile them, and to be able to apply optimizations without having to break our abstractions, without having to hard code in optimizations. We could just preserve a single representation and let the compiler do the rest of the work. To the programming languages researchers in this room, none of this should sound exotic at all. This is typically how a high-level programming language is designed. And so that was the conclusion we reached when we were designing Relay, that what the latest deep learning applications demand is indeed a high-level programming language, capable of expressing general computations. The sort of tool we would normally play with for writing the programs of our choice, but with a particular focus on tensors and tensor operators for dealing with again with the linear algebra operators that appear in deep learning models. So to be more specific about how the design looks like, we went with a traditional functional programming language design, more like from the lineage of SML, and it has all the standard features of a high-level programming language. It has first-class functions, control flow, and custom data types. Essentially, it is a fully featured programming language. You can write general programs in it, and you can also write deep learning models in it. It has some special features to support deep learning models. In particular, as I will detail further on the next slide, it has a special type system that preserves information about tensor shapes, which can be used for various analyses and optimizations in the model. Reasoning about tensor shapes is not an easy task in deep learning, and this was actually what dominated our design discussions for Relay. In particular, tensor operators have the tricky problem that the tensors you pass in can be of different shapes. The data can be laid out differently, but the resulting shape can vary based on the shapes of the inputs. This is very tricky to reason about at compile time, to reason about statically, and indeed many deep learning frameworks don't reason about it statically. They do everything on the fly. But for Relay, we saw this as an opportunity. If we can reason about it statically, we could make use of this in optimizations. And we needed to find some way to tame this complexity and have it in the compiler. And the approach we went with was to encode a system of constraints right into the type system. So we express these shape rules as constraints. Run a constraint solver, in our case, a very simple one when type checking, and we would have all of the tensor shapes statically at compile time, which we could use for implementing various optimizations. Optimizations, in turn, turned out to be easier to express. Again, when you are defining these over graphs, you can have problems. Based on high-level structure in a graph, but here we not only have scoping, functions, all of the things that give structure to high-level programming language, but we also have statically available shape information for memory planning and all of that. So we designed an interface for optimizations in Relay, namely simply language transformation passes like in LLVM and other compiler intermediate representations, or IRs. I will be using that term a lot today. And the goal here is, again, we can define these optimizations generally, which means if we can handle all of the features of a Relay program, we don't have to modify the input models. We can hopefully preserve them, not require any manual modification, and just rely on these transformation passes. It turns out to be very versatile. And in fact, we also implemented automatic differentiation as such a pass. I will not go into detail on it because unfortunately we are short on time. There's a lot to cover today. But one example application that I will go into a little bit of detail on is a fuzzer I wrote for Relay. It's an example of how the features we included in Relay made it easier to implement a traditional software engineering task that is of interest for deep learning models. A fuzzer, for those who aren't familiar, is a program that generates random test inputs for a compiler. If you can guarantee that the random inputs you generate are valid, then any errors you encounter suggest that there is a bug in the compiler. It's a wonderful tool for testing. But with deep learning models, shapes can introduce a lot of complexity for trying to generate valid inputs. You have to reason about the shapes, make sure they all match up so that you're not getting errors in the programs you generated. But with Relay, as I told you, we have constraints for defining these shape rules. Which meant I was able to use them recently. This began as a class project. It became an internship project. I was able to use these to write a fuzzer in not very many lines of code at all. And it is currently being debated by the TVM community for adoption in their testing. A neat little project with a nice little bow at the end, wrapped up with a bow at the end. Happy to say it. And I emphasize again that the language features made this possible. Relay has seen a lot of impact. I'm not going to go on too long about this because, again, it's really Jared's ball to spike. But Relay has seen plenty of impact since our initial work. It is the front end interface for the TVM deep learning compiler stack. That was the plan from the start. It has been used. TVM in turn is an Apache open source project. It has been adopted widely in industry by various companies, and it's also the subject of a startup that came out of here, OctoML. And there have been many projects built on top of Relay over the years, which have been presented at TVMcon. And one that I'm most excited about is Relax, which is the next iteration of Relay, a redesign that focuses on the problem of dynamic shapes that we can't know at compile time. I'm excited to see where the TVM community will go with it. And I hope to contribute to that work as well. I will move on. So since I told you I'm not counting Relay as my contribution, since it was the subject of Jared's dissertation, I will move on to the first project that I do consider my contribution in my dissertation, which is dynamic tensor rematerialization. So now we're moving into the middle of the system stack. This is a runtime system for reducing the amount of memory needed to train a deep learning application. A very tricky problem. In fact, we could say that memory is a very important problem for deep learning models. I told you they're all a bunch of linear algebra operators over tensors, and these tensors can become quite large. The largest models these days have literally gigabytes upon gigabytes of parameters. And over time, as this chart shows, many of my colleagues have seen this chart many times. I love to point it out. At any given time, the deep learning models that do the best tend to be those that can make the fullest use of the memory available to them. So memory is a real bottleneck for deep learning applications. The models themselves use more and more parameters, they store more and more information. But it's frustrating that the latest GPUs, that the memory capacity of the latest GPU is the best that we could do at any given time. The business decisions of GPU manufacturers should not dictate the progress of deep learning. So finding any way to reduce these memory requirements and make better use of the memory made available to us through hardware is an important is important progress for the field, as well as even for the hardware manufacturers. It reduces the pressure on them to increase the amount of memory they are making available. So to begin understanding this problem, we need to figure out where deep learning models use a lot of memory. And the bottleneck of interest in this case to me, when you are considering, let's say, a single GPU, this can vary in distributed settings, but for a single GPU, the bottleneck is activations. What are activations? Activations are intermediate values when you are evaluating a deep learning model. In order to do the updates of parameters through automatic differentiation, you have to keep around intermediate values within the model. Instead of, in any other application, you would just free the intermediate values, but here they have to hang around for the entire application until you need them during the backward pass. So they hang around for a long time, they use a lot of memory, and in fact, in the single GPU setting, they absolutely dominate memory usage for any given model. The graphs here only show two relatively small models. It's ResNet and Transformer, the original Transformer. Models developed since then are much larger than this, and I'm sure the numbers are similarly daunting. But there's good news. There are a number of techniques we can turn to for reducing the amount of memory spent on activations. And the one that is the focus of this portion of my presentation is checkpointing, a fairly simple technique of trading time for space. Instead of storing these activations for the entire computation, instead you can just free them and recompute them when you need them. A simple technique has a long lineage in the automatic differentiation literature and works beautifully in deep learning, as my collaborator Tianqi Chen demonstrated in his 2016 work on gradient checkpointing. He adopted a fairly simple approach inspired by the automatic differentiation literature of dividing a model into segments, freeing the activations in a given segment once you have finished it in the forward pass, and then recomputing the entire segment in the backward pass. This leads to some nice asymptotic behavior, depending on your segmenting scheme, where you can train a model with a linear number of recomputations using only square root of n memory. Pretty good scaling, and it has inspired many subsequent approaches. Again, it was a seminal work, inspired many subsequent approaches that came up with more intricate segmenting schemes to get better performance on particular models. And you can push this even further, as the more recent work, Checkmate, which is where the graph came from, showed. In Checkmate, rather than segments, they rematerialize individual values, and they push this to the limit. They make this optimal by designing a constraint-solving problem, an integer linear programming problem that aims to minimize the amount of recomputations for a given memory budget. So optimal, again, optimal is a pretty loud word. It's very good. And what am I doing still talking about a problem for which someone has an optimal solution? Unfortunately, optimal in this case is not the end of the story, because these approaches make use of an important assumption, which is that they plan statically. They assume that you know all of the computations in a model in advance, and this can impose many limitations. For one, more recent deep learning applications make use of dynamism and control flow and more complex data structures, and it's simply not true. You just don't know all of the computations in advance, so you can't do all of the planning. Sometimes you might be able to make assumptions and make this easier for yourself, but not in general. And more importantly, also static planning can simply be expensive. An integer linear programming solver can be slow. I believe DenseNet 161 in the Checkmate paper, they said they could not get a plan for it within 24 hours. So clearly, again, even though they can formulate it in a solver, it's not the end of the story. And there's more we can do. But my collaborators and I came up with a method that avoids the need for static planning and is still able to achieve comparable computation time and memory usage trade-offs. And we did this with inspiration from the compiler's literature. our technique is called dynamic tensor rematerialization, or DTR for short, and it takes inspiration from software caching as well as the older compiler's technique of register rematerialization, which was also the framing used in Checkmate. And in this case, we design a runtime system that makes decisions about what values to recompute on the fly instead of planning it in advance. Like a cache, it uses a heuristic to decide which values are best to free from memory, and they are simply recomputed whenever they need to be. And despite this simplicity, first of all, the simplicity is an asset because it means the model is more general. I mean, it means the system is more general. It can handle any deep learning applications, including those with dynamic control flow. But despite the simplicity, it's still able to achieve very good performance. In fact, near optimal on the models we examined. I want to show you, to illustrate the logic that DTR uses by walking you through an example. My apologies to those in the room. I have walked through this example many times, but that's okay. It makes it all the sweeter to hear it again. So what are we looking at here? We are looking at a diagram of what tensors are in memory at a given time and the computational dependencies between them. This may look like a computation graph, but I assure you DTR is not, it makes no assumption of knowing the entire computation graph in advance. This is simply the state of memory. In particular, we are looking at the tensors either in and out of memory at a given time and which ones are needed to compute which other ones. Currently, we are computing T7, but we're faced with the problem that we've hit our memory budget and don't have enough memory to compute the result. We see also that the two arguments needed to compute T7 are pinned into memory. This is a measure in DTR meant to ensure termination, that we don't have loops of recomputations. So what do we do here? We've hit our budget, and in fact, even one of our arguments is not in memory. So before we can compute T7, we need to get the argument back into memory. This means that we have to evict one tensor from memory. So now, again, we look at T5, which we have to recompute, and we see that we need T3 as the argument to recompute it. T3 already is in memory, but now it's pinned. So we need to find another tensor to evict in order to have room. Now it is up to the heuristic to decide which tensor to evict. In this case, T2 is available. It's not needed for the current computation, so we can kick it out of memory. Now we have enough room to store T5, and we recompute it. And now we're back to our original problem that we still don't have enough room to store T7. We need to evict again. Now we don't need T3 for the current computation, so it is not pinned, and we can evict it. And that's what we do. Now we can recompute. Now we can compute T7, not recompute, compute it for the first time, and the application is ready to proceed, whatever may lie ahead. So whenever we hit the budget again and have to do a recomputation, we will have to repeat this process. But I assure you, it's quite fast when it's a computer doing it and not my slides. So to summarize, the logic here is in fact quite simple. It's just a series of 4 callbacks that we're looking at, and really all we have to do is check when we hit the memory budgets. We simply call in and say, we ask the heuristic, give me a tensor to evict, then we evict it, but the greater complexity emerges when we have to actually compute the result of an operation, because we might have to recursively recompute the arguments, which in turn may also need to recompute their arguments. So there are potential hazards here. And the way we avoid those hazards is by having a good heuristic that avoids making bad choices that lead to deep recursive rematerializations. So some brief reflections on designing a heuristic. Again, here we take the caching literature as a guide. A heuristic really is a dynamic prediction of what values are least valuable and therefore can be kicked out with the fewest problems. In the case of rematerialization, there are a few special concerns. And the intuition we used is what I have listed on the slide. First of all, if a tensor is expensive to compute, if the operation takes a long time, we don't want to evict those, so we prefer to evict cheaper tensors. If a tensor has not been if a tensor has not been used in a long time, it's unlikely to be needed soon. And conversely, if it has been used recently, it's likely to be needed again. So we prefer to evict older tensors, staler tensors. And finally, of course, when you are deciding on something to evict, you want to recover as much memory as you can. So we would prefer to evict larger tensors when we can in order to have fewer evictions later. So together we can formulate a heuristic function that we try to minimize cost over memory time staleness, or together evicting the cheapest, stalest, and largest tensor. And we can actually use this formulation to discuss other types of traditional caching heuristics, like least recently used, a very, very common caching heuristic, or even just greedily prioritizing size. There's a lot you can do here. But so far, again, I've presented the overall design for DTR. I think we should start talking about what this looks like in practice. Here is a diagram, again, that my collaborators and I really love. Thank you, Alton. Yes, everyone's looking at Alton in the room. This was his doing. So this is a visualization of DTR's performance on a simplified model on a linear feed-forward network. That just means it's a straight line of operators, one feeding the other. And we can see some interesting patterns here. So to guide you through this graph, the y-axis tells us, the y-axis is a tensor ID, so it tells us that we're looking at a particular tensor, and the x-axis is a point in time in the computation. So at every xy coordinate is telling us whether a given tensor is live in memory during a given time. And the interesting pattern emerges here. We see many horizontal lines here. These correspond to individual tensors that live for a long time in the computation. And in the backward pass, we see there are filled in triangles, which corresponds to recomputing all of the tensors in between these two long-lived tensors. And what you may remark upon here is that this is actually the same logic in the traditional segmenting, as in the traditional segmenting approach of checkpointing. So our system has emergently rederived this behavior. We didn't explicitly program it in, but that's what happened. We used this to motivate a theoretical result. We proved that the distance between the segments is bounded above by a constant, that overall we have a linear number of these segments, and therefore an overall linear computation time. And that simulation was on a square root of n budget. So we have the same theoretical bound as the static algorithm, despite not using any static information. Quite remarkable. Again, I don't have time to go through the proof in detail, but it was a very encouraging result that, again, the simulation led us towards, or that encouraged us to do it. But unfortunately, we must temper our optimism, because we also proved that no heuristic can be perfect. That for any heuristic, it is possible to design a model that will force a quadratic number of recomputations, but an optimal static checkpointing method can get around it by reordering the computations. This means no heuristic is perfect, so our question instead is what heuristics work in practice. This motivated our empirical evaluation of dynamic tensor rematerialization, and here I will show you a comparison in simulation of our method against static approaches, including the optimal one, Checkmate. In fact, we used Paris Jane's evaluation artifacts directly. Major thanks to him for helping us with the implementation. So there are a lot of lines on this graph. I'll draw your attention to the one of most interest to me, which is that the heuristic I detailed to you of cost, size, and staleness, in fact, performs neck and neck with the optimal result, but we are able to compute it much faster. We don't have to wait minutes or hours for the solver to come back. It is computed in real time in milliseconds. And again, these are small models. On something like DenseNet 161 that Checkmate choked on, our approach still terminates. So it's a very encouraging result. This led us also to implement a real prototype. So this was a simulated result. We implemented a real prototype in PyTorch. And it was easy for us to do so because we were able to use the callbacks I defined earlier to do it. And this let us examine what overhead our runtime system would have in practice. We see a little bit of overhead in our profiling from naively looping over different tensors, but this was not terrible overhead. It didn't double the cost or anything, and a better implementation could potentially optimize it away. So this is a very encouraging result for us. And I want to emphasize to you that the models we looked at in this evaluation cover quite a range of models. So of course, some common ones that were used in past evaluation, but also dynamic models. Oh, that's a phone. But also some dynamic models like Unrolled GAN, which is a meta-learning application that uses second-order derivatives. Our system was able to handle it right away. No modifications necessary. Very encouraging for us. And again, this was a good place to leave off the story. That was the work we presented in our original publication at iClear 2021. Subsequently, DTR has been adopted by a couple of startups that have their own deep learning frameworks, including MegEngine. They have implemented DTR. The chart I show you is from a blog post showing their evaluation. And they got much better results than we did on the same experiment. Very flattering. They used more information in their heuristic. So I'm glad that people not only understood our original idea, but have improved upon it subsequently. More recent work has begun to consider further problems of combining DTR with swapping approaches. So again, I'm very happy to see the reception that our work has gotten. And there is open discussion on potentially implementing something resembling our prototype into mainline PyTorch. I will be very excited to see it. So there are more directions in which we could push our initial results. Perhaps I or my collaborators will be the ones to do it, but it is equally encouraging for us to see others to pick up the torch. And one final note on DTR that I want to say is that runtime systems are useful not only for these sorts of memory problems, but also the problem of batching operators in deep learning models and dynamic models. There has been recent work by Tianqi Chen and his students on this. So that is work I'm encouraged to see. And I think the motivations are similar to those as in DTR. So I will be looking forward to that with enthusiasm. I will pause here for questions. If anyone has questions about DTR, I would love to address them. Okay, if there are no questions at this time, there will be more Q&A later. So if you think of them, you are welcome to ask. Next, I want to move on to the final topic, of my presentation, which is the 3LA methodology, a project for implementing support for new accelerators into an existing compiler stack, a very important problem for optimizing deep learning applications, and one that I'm happy to say has been part of a 3-institution collaboration, hence the 3LA does not stand for anything, but on this project, we've had collaborators from Harvard and Princeton, and it has been an honor to work with people of such diverse skill sets. So returning to the earlier picture I showed you of the deep learning systems landscape, I want us to think about a more specific problem than the one I mentioned, which is the fact that these increasingly diverse deep learning applications, these are high-level concepts. I want you to think about how we talk about them, how we describe them. Sometimes people might talk about graphs of operators. You might talk about writing a program. You know, there are functions here, scope, control flow, very high level concepts. But when you are trying to lower these to accelerators, accelerators speak a very different language. You are talking about setting values in individual buffers, setting activation bits, and waiting for a signal that the hardware is done. These are very different ways to talk about applications, and yet somehow we must reconcile. Somehow we must reconcile them in order to lower high level applications to these devices. To illustrate this, I want to point to a specific device designed by my collaborator, Thierry Tambay, who you saw in Zach's highlight reel. Flex ASR. ASR is automatic speech recognition. It is a device for facilitating speech recognition applications. And Flex ASR, from my perspective, is very remarkable because it implements entire recurrent neural networks in hardware. Recurrent neural networks are models that loop over a sequence of inputs. It's very complicated functionality, and it is, so to speak, baked into the silicon here. They haven't manufactured an actual chip that does it, but this is the idea, this is the dream, this is their design. Quite remarkable. But how do you program it? You program it over a custom interface over memory mapped I/O, where you tell the device what value you want to set in which buffer, bits for which operator to activate, etc. And again, there's quite a big mismatch here in the granularity of operations we're talking about. One is talking about individual bits and registers, and one is talking about high-level mathematical structures. These must be reconciled in any compiler. And what is the reality these days of doing it? The reality these days is that a very smart person like Thierry Tambay writes a custom driver that does all of this logic manually. And God forbid you have a mistake in there. It will be up to an expert like Thierry to find it. And of course, the way to be sure, it's very difficult to get any kind of formal analysis on this because of the complexity here and the difficulty in reasoning about the hardware operations. So the result also is that these applications are very difficult to test, very difficult to validate. And surely this is a state of affairs that we would like to improve. To summarize, there are many complexities in lowering programs to accelerators. There are custom interfaces and unique protocols that you have to use just to set just to set values on the devices. You have to deal with the fact that the devices themselves might interact. They might be providing very high-level applications or potentially very high-level operations or very low-level ones. These have to be reconciled with the compiler's representation of a program, which is no easy task. And there are further complexities that I didn't even detail in the previous example, like having a custom numerical representation. Again, this is further complexity for the compiler to deal with. And the result, again, is that experts are needed to handle all of these problems, and every solution is sui generis. And again, our aim in the 3LA project is to have a more systematic solution for taming this great variability and providing an established flow for reconciling all of these difficulties. I hope to convince you that we have made a major stride in doing so with the insights, again, based on the compiler's literature, with the insight that what is most lacking here is a way to formally describe the semantics of accelerators and the operations they provide. What is most missing here is essentially an instruction set, which is something we would take for granted when compiling to any other device. And our approach in 3LA is to provide such a specification for accelerator operations and show how we can adapt traditional compiling techniques to lower arbitrary programs down to these devices, and in fact to make this process look systematic, to make it look the same for every device we consider. As it happens, the interface itself is past work. It was the work of my collaborator, Dr. Boyuan Huang, who designed the instruction level abstraction, which, as the name suggests, it is an instruction-like representation for accelerator operations. An ILA for a given accelerator is defined as a state transition function, which describes how each accelerator operation affects the architectural state of the device, which is, again, this is exactly how you would define an instruction set for a normal device, for a normal programmable device. And what's nice about these abstract instructions is that they map very closely to the actual hardware operations provided by the accelerators. So this interface maps neatly on top of the memory mapped I/O interfaces that the accelerators expose, and is therefore excellent to use as an intermediate representation for compiling. There are even more benefits that come from the ILA. This is again the further work of my collaborators at Princeton. They have developed a tool chain called iLang, which provides additional support that make use of the formal semantics that are provided in an ILA specification. For example, given the semantics for a particular device, iLang can generate a functional simulator for the device, which will run much faster than a circuit level hardware simulator. So this is very useful for testing, and as you will see, we make extensive use of this capability. You can also lower the ILA semantics into solver domains like SMT and begin to do formal reasoning about it, do logical verification, which we will also do in our evaluation of the methodology we designed. So to summarize, what I have just described suggests a clear methodology for implementing a compiler, where you start with your high-level language, a domain-specific language describing your model. You find portions that you want to accelerate and output ILA instructions that can be lowered to the device. And then you can either lower those ILA instructions directly to invocations of the device, or you can call a simulator to do testing, or you can do formal verification using a solver. So these are all wonderful capabilities. And what's most important here is we have now a clear middle layer, which means that a hardware expert can just help you write your specification. And once you have that specification, you can focus on the problem of compiling to it. You don't need all the expertise throughout the entire system, as you might if you have some kind of ad hoc driver that does all of these tasks all at once. And a further benefit is that having the ability to simulate here is, again, massively helpful for testing and development, which can facilitate everyone's dream of hardware-software co-design. So there are some wonderful benefits here, but I have left out a portion of the story, which is the question of mapping to mapping operations to accelerators. How do you know what portions you can accelerate? There are many complexities here. When you have a big program, you can have conflicting choices. If I choose to accelerate one operation, that might block me from accelerating another. I might have more than one accelerator to choose from. Oftentimes, you can have multiple accelerators on a single chip. So there are many choices here, and we need some way to reason about them. Past work has given one way, a very simple approach, which is simply do syntactic matching on your program. In the Bring Your Own Code Gen framework in TVM, you can do just that. You can specify a pattern in the language saying this is an operation that is supported by an accelerator. And then TVM just does pattern matching. It finds instances of this operation. It does tie breaking arbitrarily. I don't remember off the top of my head if you can customize the tie breaking, but it'll just find what it finds. It puts an annotation there, and then it hands it off to the user. It says, okay, I found your operations. Please give me a code generator. So here you could use a custom driver, for example. It's a very flexible approach and one that has been enthusiastically adopted by the TVM community. But this approach can run into problems. Oftentimes, there are many equivalent ways to express the same computation. There are many equivalent ways to express the same computation, and listing all of these equivalents can not only be tedious, but also error prone. You can forget to list one, you can incorrectly list one, and it becomes, again, a game of cat and mouse in terms of exhaustion. But more importantly, as the patterns themselves, as the operations the accelerators support grow more complex, the patterns become larger, which means there are even more equivalents to have to chase after. So manually listing equivalent patterns is not a tenable approach. And what would be nicest is to be able to reason about this together to get all of the equivalences. Here I have drawn upon the work of my collaborators, as well as actually the past work of my advisor, in the use of term rewriting for this kind of reasoning about equality. If you have a term rewriting system, you can have rewrite rules as your axioms. So you have a rewrite rule for each equivalence. And then you apply rewrite rules until you can transform one computation into the form you are looking for. And if your search is complete, you will never miss what you're looking for. But naively applied, if you just apply rewrites immediately, you can run into the problem that the order matters, that the order in which you apply rewrites will prevent you from doing other rewrites that might prevent you from finding what you're looking for. There are many ways to deal with this. You can come up with canonical representations. But the approach we stuck with in 3LA aims to sidestep the problem of ordering altogether, namely through the technique of equality saturation, which turns these term rewriting problems into search problems. This is done through the use of an interesting data structure called an E-graph, an equivalence graph, where rewrite rules become graph transformations. You introduce equality edges into the graph, as the example is showing. And what's important here is as you add more rewrites into the graph grows, but you are not destroying anything. All of the representations are present at the same time, but this representation can be kept compact by deduplication. So you don't repeat nodes. If a node's already there, the graph doesn't grow, which means a single graph can actually represent an exponential number of possible rewritings. It's very handy, and this means then that finding the specific instance you're looking for is a question of searching through the graph of extraction. There are many ways of dealing with this. My colleague Max Wilsey, who's in the audience, has developed a library for performing this process at large scales and at high performance. That's Egg, whose logo I have at the bottom there. It's a nice process, and we were able to adapt equality saturation to our problem through the use of Glenside, an intermediate representation developed by my collaborator Gus Smith, for tensor computations. So it's a representation for tensor computations that lets us perform these kinds of rewritings efficiently. And in the context of accelerators, all we have to do is get a representation of our program into Glenside, add rewrite rules for the accelerator operations that we support, and let equality saturation go until we can find all the rewritings we want. Finally, leaving us with an extraction step where we take the final E-graph and get a candidate program out. There are many questions of what the best candidate would be. For our prototype, we used a cost function that simply looks for as many accelerator operations as we can find. But in real applications, you would want to get the candidate that has the best performance. So you would want a cost function reflective of real world performance. We'd leave that for future work. there are many considerations there. Predicting performance is a very tricky business. So taking a step back, we have now this overall flow. We implemented a prototype for deep learning applications using our technique, where we start with programs in Relay representing deep learning applications, and those programs might be imported from other languages, from other frameworks. We translate them into Glenside, apply equality saturation, and then finally, when we have matching patterns for accelerator operations, we lower those into ILA instructions and make use of the various capabilities of ilang to execute and simulate these. So I want to show you some of our results. Okay, yes, I think we're short on time. I want to show you some of the results. I'll wrap up soon and let you ask questions at me, hurl things at me, all those nice things. So we supported 3 devices in our prototype. We're currently working on getting more. These 3 devices have quite a diverse array of capabilities. One of them is FlexASR, which supports entire recurrent neural networks. Another is HLS-CNN, which it does one thing and one thing only, convolution operators, and it does it well. And we also targeted VIDA, an accelerator designed at here at the University of Washington, which is different from the others because it's programmable. It already has an instruction set, and we included this to show the generality of our approach, that we can also handle devices that are already programmable without needing to introduce a new level of programmability. And to support each of these devices, there are conceptually only 3 steps in the methodology. First of all, you need to come up with the ILA specification, and the rest after that, so to speak, is boilerplate. All you need to do is add rewrite rules for the accelerator operations, and finally have some code that will take the ILA instructions and lower them into the real device instructions. In the case of FlexASR, the last part is exactly what we did. We simulated FlexASR on an FPGA, which again wasn't an easy task. You can ask Thierry about that part. And we were able to lower a linear layer operation all the way from TVM to FlexASR using our methodology, and the lights on the FPGA blinked and everything. It was nice. It was very gratifying to see it happen. And I emphasize, it's not easy. Thierry did not have end-to-end compilation on his own. He had the custom driver he wrote, but he couldn't take a model from a deep learning framework and have it really run on the device. So this represented progress. For bigger models, for other applications, we didn't run it on real FPGA implementations of the devices, but we ran it in end-to-end simulation. And this already also is beyond what many devices or beyond the capabilities of many device developers. It's very tricky to run end-to-end simulations, precisely because it's so hard to hook accelerators into frameworks. So this was already a big achievement. And in fact, we ran multiple applications all end-to-end through simulation. We had a surprising result that the results didn't match. This is bad. You want the results to match. You never want it to be the case that, you change devices and now the results are different. So why did this happen? It is because of custom numerical representations in the devices. We don't have a perfect answer for dealing with custom numerical representations, but our simulation capabilities helped us address these problems in these specific cases and suggests perhaps how future work might grapple with these numerical issues. We were able to do some profiling thanks to our simulation and figure out what operations were causing losses in accuracy. This led us, in the case of HLS-CNN, to conclude that we had the data type was just too small. We had too few bits. It couldn't represent the range of values we needed. So expanding the data type fixed the accuracy issue. In the case of FlexASR, we have not fully solved the dynamic range issues that we encountered, but we are quite confident that dynamic range is the issue, that the data type cannot represent the range of values we need. This is suggesting possible mitigations, which might even include using a different model. Maybe we had the wrong model for the job. This is an important conclusion to come to and very important when you are developing a device. And because we can do this in simulation, this is now available at an earlier point in the device's life cycle. I would call this a very important capability. Finally, the last results I will briefly discuss because it's still ongoing work. The last results we have are in terms of formal verification. We have used the ILA semantics to formally verify the mapping of one operator, the max pull operator from relay to the flex ASR implementation, confirming that the software implementation in TVM matches the hardware implementation in flex ASR. It's a useful capability. We only did it for one operator, so we would love to keep scaling this up to make this, to parameterize this over all possible input sizes, for example. There are many things we would want to do, but we have a proof of concept, and this suggests that our methodology could allow for end-to-end verification of the entire compilation stack. There are more steps, of course, involved. We would have to verify the rewrite rules. We would have to formally specify more of the input language, but the foundations are there. This is a very exciting capability considering how tricky accelerators are to reason about. So I hope future work will continue to pick up on this. Of course, there are many ways that we could keep scaling up this work. But I'm excited about the results we've already shown, and this work, as I said, is ongoing. I hope to continue contributing to it personally, and my collaborators, I trust, are equally enthusiastic. So that concludes the topics of my dissertation, this survey of the systems landscape for deep learning, and I want to leave you with some concluding remarks. That so far we have observed many intersecting trends when it comes to deep learning systems and hardware broadly. We've seen the rise of hardware specialization, which creates many complicated problems on the software side for systems and compiler support. But there are also many important trends in deep learning applications that they are addressing more complex problems with more complex model architectures and more expressive features, which systems must similarly support. This new era of computation has placed many demands on systems designers and implementers, including support for, again, these new accelerators and support for hardware-software co-design, designing accelerators to support the specific applications in mind and making sure that they can do so at the appropriate economies of scale. Of course, deep learning continues to be again, an immensely productive intellectual lineage. Every year, the new advances are staggering, and it is the task of systems designers and maintainers such as myself to keep up with them. But I contend we are not helpless in this journey. The programming languages and compilers literature, as I hope I have shown to you through the work I personally have done, and I can assure you it's only a small example of the work being done by many, many others on many, many systems. The compilers and programming languages literature provide many precedents and much guidance for dealing with this increasingly diverse landscape. And the reason for that is because programming languages excel in providing abstractions. In a sense, programming languages is the study of abstractions. And the strength of abstraction here is generality, that we can make fewer assumptions about what deep learning models look like. We can make fewer assumptions about what the hardware they run on looks like. So I hope that these techniques will continue to guide us as we design systems to support the applications of the future. I am pleased to say that I hope to continue to work on these problems. The story isn't over yet, and I personally will continue to work on deep learning systems when I begin work at OctoML as a SysML engineer, and I hope to continue contributing to TVM. Thank you all very much. Thank you all very much for listening to this survey of my work. Indeed, the survey of, I could say, the last 5 years of what I've been working on. It's been very exciting. There are many people to thank for getting to this point. In particular, I have here all of my collaborators at the University of Washington, many of whom are in this room or in the Zoom call. I have this picture arranged roughly in chronological order. It's been a long journey and a very difficult one at times. But at the bottom, I have the people who already have their PhDs, the so to speak adults in the room, who have provided much valuable guidance to me, especially Jared Resch and Tianqi Chen, who I would say introduced me to this domain of deep learning and more importantly, gave me a vote of confidence when I wouldn't have given it to myself. For that, I thank them. And whether I am fit to join their ranks, I leave it to the committee to decide. And I'm also grateful for my collaborators at other institutions in this 3LA collaboration. It's been very exciting to work on that for the last 2 years. The results we already have are exciting, and I think we have some interesting plans in store. I hope to continue working with them, and I love having a renewable excuse to visit Princeton whenever I want to. I'm very grateful. And all of the work, I want to say one last note, a word from our sponsors. It's more than just a word from our sponsors. All of this work was supported by the Ada Center, not just financially, but also intellectually. There have been many productive gatherings of the Ada Center. I've met many hardware designers. In fact, you could say the 3LA collaboration came out of the Ada Center. So I would call that a very important portion of my doctoral experience. And I'm very, very grateful to have had the support of all the scholars in the Ada Center throughout my work. And finally, thank you all for attending. I would be you could delight me the most by asking incisive and pointed questions about the work I've presented. Thank you very much.
Ooh. Okay, there are a lot of clap emojis in the Zoom as well. Let's go ahead and open it up for questions. So if folks want to unmute and ask, or type up here in the room, or type something in Zoom, would be happy to handle any of those. But yeah, please, Max, go ahead.
Thank you.
Great talk, obviously. The DTR work is super interesting. It's like your classic time-space trade-off. And the fact that it works so close to optical in the domain that you used is a fantastic result. Could you use it in another domain, perhaps some sort of like pure functional programming?
Excellent question. So in case that didn't come over the microphone, the question from Max is whether we can use something like deep learning in another domain, because the time-space trade-offs there certainly have the air of generality. And DTR, yes. They certainly have the air of generality that we might consider other functional programming domains here. It's a great question. My collaborators and I have thought extensively about it. And truth be told, we don't have a slam dunk example, unfortunately. The main characteristic we have articulated, why DTR is so useful for checkpointing, is because in deep learning applications and in automatic differentiation, you have values that have to live a long time in the computation, but you don't use them for most of that time. We have not found, again, a slam dunk example of another application that also has this characteristic. I know my co-author, Marissa, I don't know if he's in the Zoom call. He's in Utah, so he's not here physically. My co-author, Marissa, has been looking at web browsers as a potential further domain. I do not know of his progress with web browsers. There might be some classical AI techniques that also have this characteristic. We have not explored them, but it would be interesting. One other tricky part here is in DTR, we're talking about managing individual tensors. The tensors themselves are huge, which means that any auxiliary data you have to manage them is going to be minuscule compared to the tensor itself. In other domains, the values might be smaller. So you might be spending too much memory in order to save memory. So that is a concern. So ideally, something where you're managing tensors would be the ideal.
All right. We also have a question from the Zoom. I think Chandra has her hand up.
Please do.
Can you guys hear me?
Oh, we can't. Okay, I'm going to turn my volume on.
Go ahead, Zach.
No, it is up. I can't
Can
hear
you hear
her.
me?
Is that a microphone issue? She's not speaking.
Can other people in the
Oh,
Zoom hear her?
I can hear you,
I
Chandra.
can't hear you, Chandra. I'm sorry.
I can hear you too.
You can
Okay.
give the question through text.
But looks like the room cannot hear you.
There we go.
Oh, can you hear me now?
Yes.
Oh, cool.
Can you turn off your sound?
All right. So yeah, Stephen, great talk. And my question is about somewhat towards the end, you talked about formal verification in regard to 3LA. And one of the things you said there was you wanted to verify the rewrites themselves. And I just wondered if it's possible to use something like Ruler to automatically generate the rules. And is this something like, what is the complexity of the rules and what kinds of rules are you usually using? Just to understand if it's actually possible.
Great question. Sorry, we had an echo. Ready now? Okay. Yes, great question. We, in fact, in our latest archive post on this, we actually mentioned Ruler. As far as verifying rewrite rules, we really would want, SMT verification of the rewrite rules. I guess Ruler, if I recall, it does have a step where, Ruler does have a verification step. So yes, we would love actually to get rid of the step where you have to manually specify the rewrite rules for accelerators. And we think something like Ruler might be viable for this, because the rules we want to add, really, it's a rule of the form, some operation in Glenside maps to one accelerator call. Those are the rules we want to add. Certainly seems viable. So what you would need to find is just what expression in Glenside matches the accelerator. I trust that these can be small expressions, which means an enumerative approach would find them. That's what we would be banking on. We haven't tried it, of course, but it would be lovely if it worked. I think I have a slide actually that illustrates some of the other rewrite rules we're using in the project. So this is just from Glenside in particular. I didn't have time to go over Glenside in detail. I went over time as it was, but I think I have an example of some of the rewrite rules. I think these are the operators in Glenside. Okay, I don't have a, there's one example of a rewrite rule. So this is a rewrite rule for targeting a systolic array in Glenside. So this is what we would want. The systolic array is a type of accelerator for matrix multiplications. So the right-hand side of the rule is a systolic array as a call to the systolic array function. The left-hand side is the computation expressing a matrix multiplication. I think that's what it is. That maps to it. Yes, that is a matrix multiplication in Glenside. So these would be the types of rules we're looking to add.
Cool. Okay. Yeah, I think with some of the stuff that Brett is doing, I wonder if this would be possible. But yeah, it's very cool.
I think. All right. Well, if we ever figure out the microphone, that'll be the next PhD. Any more questions from the audience? We have gone a little over time. I know there is some pressure.
Question in the chat.
Oh yeah, Anna, go for it. Do you want me to read it or?
Please.
All right. Anna is asking, wonderful talk, Stephen. I find myself wondering a variant of what isn't deep learning. PL techniques such as compiling and specifically verification typically imply 100% correctness, while imperfect but very high accuracy seems to be a feature of any learning. How do we identify situations and software that require verification and 100% correctness despite the rise of deep learning?
Oh man, this is
my mic was muted, not my speakers. Now
yes, yeah, Anna, you hit the nail on the head there. This is one of the toughest problems we are dealing with in 3LA, and actually something where we have to try to convince reviewers of this, that formal verification, when you are dealing with domains where correctness is approximate, it can still have meaning. So yeah, there are many perspectives to offer on this question. For example, we've seen in deep learning that changing numerical data types, the technique of quantization, changing numerical data types can still lead. It can be a useful optimization, even though in the traditional programming language's sense is not correct because it changes the semantics of the program. This might also be a question of abstractions. What is the right abstraction for expressing deep learning applications? Perhaps we have over-specialized. By talking about real numbers in the mathematical abstraction, we've over-specialized it, that in reality, a much more permissive representation is more accurate. So there's a question of abstractions. What is the right way to discuss these? When it comes to implementing the models themselves, again, reasoning about quantization has been, that's a massive research area unto itself, quantization in deep learning, the degree to which you can vary input data types and still have a final application level result that's correct. It's very tricky. There are many techniques out there. I think the approach in 3LA that we've so far settled on is to rely on the empirical approach. Use simulation, see what works out, and go from there. When it comes to formulating formal rules for reasoning about these kinds of approximations, that is definitely. I would even say, I would go so far as to say the committee can harangue me if this is a cop-out, but I think that's a subject for another PhD. I would love to discuss this further with you, Anna.
Let's do microphone swap. Maybe. Okay, Anna has said fascinating, thank you. I also know we have several folks from outside UW. If there are any more questions, now is the time to get them in. We will next be moving to a closed session for what I believe is colloquially known as the snake wrestling portion of the defense. Any additional questions from the audience, either in Zoom or in person? All right, well, let's thank Stephen once again for a great defense talk. And I think with that, we will ask everyone who is not on the committee to please depart so we can release the snakes or something. I don't know what to write.
I think it's my usual